Section 7.4 is the division property of exponents. I can divide polynomials with the same base, and I can raise a quotient to a power. Big ideas here. Properties of exponents can be extended for division of powers with the same base. To divide powers with the same base, we subtract the exponents. To raise a quotient to a power, we raise the numerator and the denominator to the power and simplify. So these are going to be very similar to what we did with multiplying powers with the same base and when we took a product to a power. A lot of the same concepts here. Take note on page 439 talks about dividing powers with the same base. To divide powers with the same base, we subtract the exponents. So here, we can rewrite example 1 to simplify this if we wanted to by moving our denominator to our numerator and changing that to be a negative exponent. Now, since we're multiplying powers with the same base, we can keep our exponents, or keep our base, add our exponents. Common denominator is 2. So I'd have 5 plus negative 4 over 2. 5 plus negative 4 is 1 over 2. Okay, we can skip this step though of moving from the denominator to the numerator and use a property that's very similar here. We can divide powers with the same base. So instead of having to move that up as a negative 2 and add a negative number, we can just go ahead and subtract right away. So 5 halves minus 2, which again I'm going to write as over 1. Common denominator 2. Whatever we do to the bottom, we do to the top. 5 halves minus 4 over 2 gives me 1 over 2. So either way, we get to the same place. So again, when we divide powers with the same base here, our bases are the same, we can go ahead and just subtract our exponents. Same idea here in B, but remember that we have to keep our bases the same. So we can put together our m's, and we can put our n's together, but we can't combine things with different bases. So here I can take m to the 2 minus 5 and n to the 4 minus 3. Numerator minus denominator's exponents. And again, we keep those bases. 2 minus 5 is negative 3, and 4 minus 3 is 1. I'm going to simplify here. I can't have that negative exponent, so I move it to the denominator. And in my numerator, I just have n, or n to the first power, and that is my solution. Again, I can't combine those any further because I can't combine things that don't have the same base. Feel free to pause here and give these a try if you'd like. We're going to find the simplified form for each expression. Here, I'm dividing powers, same base, so I keep my base, and I go ahead and do 3/4 minus 1/2. Numerator minus the denominator. And it's like we bring that up as a negative exponent and add. Here, common denominator is going to be 4. 3/4 minus 2/4 gives me just y to the 1/4 power. Again here, I have the same base, so I keep my base. And to combine my exponents here, since I'm dividing, I'm going to go ahead and subtract. 7 halves minus 3 over 1. When we subtract and add, we need a common denominator. Here my common denominator is 2. So 7 halves minus 6 halves gives me d to the 1/2 power. See, I can combine like bases. So I can put my k's together. I can also put the j's together. For the k's, I keep my base. And since I'm dividing powers with the same base, remember my exponent, there's a 1, I'm going to go ahead and subtract them. 6 minus 1 is 5. I can do the same with my j's here. I keep my base, subtract my exponent. So I have j squared right now, and I'm going to subtract 5. I get j to the negative 3rd power. Now, we don't want to leave things with negative exponents, so I'm going to go ahead and move that to the denominator. My k stays in the numerator because it has a positive exponent. My j moves to the denominator to make it positive. D, same idea. I have a's I can combine. I keep my base, subtract my exponent. So numerator minus denominator's exponents. I can combine my b's. Numerator minus denominator's exponents. Keep my base, 5. We want it to be simplified, which means all of our exponents need to be positive. So I move the 8 to the denominator and keep my b in the numerator because it's already positive. E here, we have a few different bases. So I'm going to keep my x's together. I'm going to keep my y's together. And I'm going to keep my z's together. Again, we can only do this if they have the same base. So for my x's, I have 4 in my numerator. Since I'm dividing, I'm going to subtract 4 in my denominator. I get x to the 0 power. For my y's, I have -1 in my numerator. Since I'm dividing, I subtract exponents, a -5. Here, when I subtract a negative, I really just add. So I have -1 plus 5, or 4. And for my z's, in my numerator I have 8. I subtract the 1 from my denominator and get 7. Final step here is to simplify if we can. X to the 0 power is just 1. And we're just multiplying here, so 1 times y to the 4th is just y to the 4th, then times z to the 7th. In example 2, we're dividing numbers in scientific notation. Population density describes the number of people per unit area. During 1 year, the population of Angola was 1.21 times 10 to the 7th people. The area of Angola is 4.81 times 10 to the 5th square miles. What was the population of Angola that year? We're looking for population density, and here it tells me population density is the number of people per unit area. People per unit area. If we look here, we have 1.21 times 10 to the 7th people per 4.81 times 10 to the 5th square miles unit area. So miles squared, for example. Here, I can go ahead and divide my numbers. Here I get 0.252 approximately. Now, I can divide my powers by keeping my base and subtracting my exponents. So I get 0.252 times 10 to the 2nd power. Now, I need to put this in scientific notation. So I need to have exactly one number in front of my decimal. So 2.52. And in order to do that, guys, I have to divide by 10. So here I'm going to subtract 1 from my exponent. So times 10, which we could do is 25.2. Can't have 0.2 people though. So 25 people per square mile. Now, during 1 year, Honduras had a population of 7.33 times 10 to the 6th people. The area of Honduras is 4.33 times 10 to the 4th square miles. What was the population density of Honduras that year? Remember, population density is the number of people per unit area. So here the number of people, 7.33 times 10 to the 6th. And our area is in square miles, 4.33 times 10 to the 4th square miles. Here, when I divide, I get 1.69-ish times same base, and when I divide powers with the same base, I can subtract my exponents, and I get 10 to the second power. Now we're looking for the population density, and if I say 1.69 times 10 to the second people per square mile, not very helpful. So I'm going to go ahead and actually take 10 to the second power, which is 10 times itself twice, 100, and multiply it by the 1.69. And I get 169 people per square mile, or mile squared. Take note on page 441 is raising a quotient to a power. To raise a quotient to a power, we raise the numerator and the denominator to the power and simplify. So when we're raising a quotient to a power here, very similarly to how we did it with a product to a power, we take all of our bases inside. So here I have z to the 2/3 and 5, and I give them our exponent. Big thing here is that we keep them in the same part of the fraction that they're already in. So here, since I have one base for my z and a power raised to a power, I multiply those exponents. We multiply straight across. We get z to the 6/3, or z squared. In my denominator, I can take 5 to the 3rd power here. 5 times 5 times 5 is 125. So I get z squared over 125. Now, feel free to pause here and give this a try if you'd like. We have a quotient, 4 divided by 3 to the x power. So here I take each of my bases, just like we did with products, and I give them the exponent from the outside of my parentheses. It goes to everything inside my parentheses. 4 squared is just 16. In my denominator, I have a power to a power, one base, two exponents, so I keep my base, and I multiply those exponents and get to the 6th power. In example 4 here, there's quite a bit of stuff going on. So we have a couple options. We can either take that exponent into everything first, or we can get rid of the negative in the exponent first. And that's what I'm going to do. So in order to get rid of the negative on my exponent here, we've got to completely flip that fraction. So the 2x to the 6th is going to go to the bottom. The y to the 4th power goes to the top. And we change our exponent to be positive. It's like we move the whole thing down, but when we divide with fractions, we multiply by the reciprocal. So we just take the reciprocal of everything inside the parentheses there. So here, I can take my bases, y to the 4th, 2, and x to the 6th, and they're all going to get my exponent. And we can reduce. Power to a power means I'm going to multiply my exponents. 2 cubed is 8, and power to a power again means I will multiply my exponents. If you would have distributed your exponents right away, they all would have been negative, and you would have just moved them all to the opposite parts of the fraction. On the last example, I made made my exponent positive. Here, I'm going to show you the other way, just by getting the distribution first. So I'm going to take each of my bases to my exponent. Now, when we have negative exponents, we have to move them to the opposite part of our fraction in order to make them positive. So my a is going to end up in the denominator squared, my 5 is going to end up in the numerator squared, and my b is going to end up in the numerator squared. And I take 25, 5 squared, b squared over a squared. And that's my final answer there. Quick recap. Properties of exponents can be extended to division of powers with the same base. To divide powers with the same base, we subtract the exponents. And to raise a quotient to a power, we raise the numerator and the denominator to the power and simplify. Again, if we have negative exponents on the outside, we can either make it positive first or distribute it in and then make it positive. And that's what I have for section 574.